Okay, welcome everybody to the last lecture of this edition. Actually, this is the 9th edition of a lecture. What we are going to do today is to do a kind of summary of what we have seen today, and this will be done by me in the next 40 minutes. Then we will have a lecture from Yulia Sandaradmitskaya from the Institute for Neuroinformatics in Zurich, which is it is a joint institute in between the University of Zurich and the ETH, which is the Polytechnic of Zurich, which is both are very good institutions doing very interesting research. So as told, so this is so first part until 10:15 will be a summary. So we will try to see what to summarize what we have seen so far. And the second one will be actually an interesting lecture on not just neuromorphic computing, which is an interesting topic by itself, but about how dynamic models of neural dynamics for embodied systems can be implemented by a neuromorphic computing architecture. So this is very interesting because almost 10 years ago, when Rolf started these lectures, many ideas were ideas, so were at a conceptual level. So the idea, the great contribution by Rolf and others was to see that, look, we are building robots in a way which is quite different from the way natural, intelligent agents work. Almost 10 years later, we can see that we are doing significant progress towards implementing in the real world this kind of things. Because you should have seen, for example, from last week's lecture, and you will see from the guest lecture of today. So as told, this is a summary, so you will see something that we actually introduced in the first lecture. So we know that we are living in as Confucius put it, in very interesting times, because we are experiencing a dramatic expansion of our economy, of our society. So under many respects, we are having a lot of success. So in the last, thanks to the formerly developing countries, I think more than 1 billion people left poverty in the latest 20, 30, 40 years. So this is a tremendous positive thing, tremendously positive thing. On the other hand, we are actually dramatically put in danger the ecosystem, the planet ecosystem that we actually sustain ourselves. So we have this problem that we know that there will be about 10 billion people on this planet 20 years, 30 years in the worst case. So not a very long time frame if you think that you need a lot of new infrastructure for these people. And 20, 30 years, despite the fact that we say that everything is fast, 20, 30 years are at the level of a state is almost tomorrow. So it means that we are very close to a crisis situation. And you know, that so far, the main impact that we have had on the planet is the so-called greenhouse effect. Unfortunately, the level of CO2 in the atmosphere is such that it is really changing the climate of the planet in a way that can be mitigated. And you know that there have been a few days ago in Katowice in Poland, there have been a huge international conference organized by the United Nations on this topic to try to define some shared policies to cope with this problem. And you know that the result was mixed. So if you think to this, that I think if you remember this slide that I've shown the first day, so this story of the 2 degrees of the Paris Agreement is a serious issue because it's, of course, we don't know if it is 1.5 or 2.5. 2 is an estimate, 2 degrees Celsius of increase of the average temperature of the planet, which means that in some places you may even have colder temperatures. In other places you may have much more than 2 degrees. But what is really captured in this graph is that as so this might be a bias of a roboticist, no? The fact that we tend to see the Earth system itself, so the planet itself as a self-regulated homeostatic system. And if you take this stance, so you see how a concept which is typical of control engineer can be used to understand what's going on in the climate evolution of Earth. So that's why you should never think, a legacy from the 19th century is that we have all the academia and even the society organized by strict compartment. No? So there is physics, there is mathematics, there is philosophy, there is biology, there is engineering. While the reality don't know the world, the universe know nothing about our classification of problems. So an idea coming from the study of dynamical systems like this one can be used to understand what will happen to the planet when, as we know, the level of carbon dioxide will grow, because it will grow, it's still growing. And what we see is that we have basically a number of limit cycles. You remember that I was talking about the importance of limit cycle in passive working. Limit cycles are typical of any dynamical systems, and in particular of a climate system. You see that we have several possible equilibrium limit cycle of the Earth system. There is one which takes back the Earth more or less where we are now, but there is also one which goes to very high temperatures, so to +8, which means tens of meters of sea level increase. So we really have a lot of problems. And that's why I say this, because robotics and AI, if you want to, you mean, I was talking about disciplinary compartments. Actually, even robotics, so the body of intelligent system, and AI, the mind, so to speak, of the intelligent systems, are more or less two disciplines. And one of our main point here is that they should not be, because they are not in natural disembodied mind. So we only know of animals where the two things goes hand in hand. So however, if you look at what has happened in robotics until very recently, we see that for the very early examples of a renaissance, but a lot, or even before. So 5,000 years ago, there was some tiny robot called the South Chariot, built by some Chinese as a way to measure distances and keep and remembering the position of the south. So a robot alternative to the compass. But if you look, so this was a state machine, a clock, that if you are not, the simplest approximation of a state machine is a clock. So a system which passes from a state to another following a deterministic procedure, connected to a physical actuation. In the case of the old times was gears and pulleys, and the state machine was a clock. So typically other gears with some nice spring or other mechanisms to give you energy, and some special mechanisms which are kind of strange gears, if you want. To recent times when we have even androids, and the androids are can be extremely convincing in terms of appearance. The principle is the same. So we have a big state machine. In the case of an android, it's a very big state machine. In the case of a clock, it cannot have many states. We have seen, but a quantitative difference is many times qualitatively relevant, because when basically we started to use microprocessors, and I'm saying in the 60s, so in the 60s, if you think that, if you go back for the younger people, like typically students, if you think that every year from those times, we have doubled every year the computing power for unit of cost, so to speak, so the Moore law. So even in the 60s was already possible to build robots. These kind of robots that you see here, and these kind of robots are today ubiquitous in the factories. And this was done by using mechanical engineering, so the science of how to study the trajectory of a thing like this, and also how to study the stress on a thing like this, so to study if a bridge go down, or computer science, so the science of writing algorithms, where I mean, typical example, sort algorithms, or sort find the maximum of this series of numbers, or search algorithms, find the record with these parameters equal to what I'm looking for, and control engineering. So basically the science, typically linear control engineering. So the science of keeping the science of thermostats, if you want. So you want the temperature of 20 degrees in your room, and you give more fuel to your heating system when you go to 19 and you give you push less if you go to 21. So this is simple. You know, people who are studying, students studying this know that is. So it's simple in principle, like many things. In practice, you need to study some formula, but the principle is, so basically we have mechanical engineering, so how to study trajectories of things and how to study if things structure are strong enough not to break, for example, when they move. No, think to the wheels of your car, why they don't fall apart. They are how to write algorithms and the science of thermostats. This allowed a tremendous use. If you look at that graph, you see that increasingly robots have been using in factories, but they have been used in typically for welding, for painting, for things like that. What happened not a lot of time ago, probably also because now we have enough data, because there are a lot of data in the web, for example, and for example, the indexes, the search engine like Google are basically Google or Baidu or whatever, or other systems around, less popular, so to speak. They typically are big computer farms, so many computers connected, storing an index of the web. So this means that we have a lot of data stored in different places. This also has some political implications, if you think about it, because means that some companies have a tremendous level of, a very detailed level of knowledge on what's going on. And this has been controversial. So, of course, we need search engines, so that's okay. But the fact that these companies are private and are not in every country is creating some conflict, you know. Joanna Bryson was talking about some radical solution that you can implement on it. Anyway, having many data and having a lot of computing power, because now we have, I think, still not the same level of computing power of our brain. We are still far away from the computing real computing power of our brain. But we have a lot of computing power. So things like machine learning, which is basically a statistical method to approximate function and predict their future values, and the Internet of Things, so which is internet that now is so cheap because radio transmitters and communication chips cost very little, so you can put them on in a TV set and whatever. And some application of artificial intelligence, like we didn't go a lot into this, but the typical simple logic to put a series of things one above the others. This is actually sparking a new dramatic wave of adoption of robots, because now we can change, so vision systems are not very good for a while, but they can work very well in a factory. So a lot of things that formerly were not, or can drive a car, assuming that you have some infrastructure in your city or on your street. And this has led to this dramatic what is so what we have seen is that, however, not everything is possible in this framework, because there are limits in So you know, this was the state of the art, and it is more or less the state of the art now of humanoid robotics a couple of years ago, when DARPA organized this challenge to do very simple things like opening a door, sitting in a car. So all things that for us are trivial. What we have seen is that for a robot, this is extremely difficult. And and those results are even then more impressive if you think that they also studied during the challenge how many people were working behind the scenes on computer teleoperating the robots. That number is above 10, and the minimum was 9. So this means that if you want to have, so you need 10 engineers to obtain this kind of silly behaviors overall. So why? So the idea is that this is, so of course you may think, okay, we need more complex code, we need even more computing power, we need a more complex mechanism in the arm, in the finger. So you may think that you need, these machines are already complex. I mean, cost-wise, if you want to think in terms of costs, those robots cost 1, 2, 3 millions of dollars or euros or whatever each, or which means translated to hundreds of millions of yens or 10 of millions of renminbi. So I mean, the cost itself shows that they are very complex. They have hundreds of components. I mean, if you compare a luxury car cost to one of these robots, you see that one of these robots is more expensive than any Ferrari, any super expensive car. So they are almost expensive like a small airplane. So they are complex. Also from this, you see that they are very complex. And the problem is, so we need even more complex machines. It's a question. Huh? No, I was talking, today I really wanted to do a kind of a summary of what you have seen. So if you look, for example, as told, these lectures are meant as stimulating lectures, so hopefully. So the idea is that you should check the literature, you should think by yourself, and as told many times, me, the guest lecturers, my colleagues are very happy to interact with you if you have questions, if you have doubts, if you have proposals for project. One of the papers that I think is interesting to read for everybody is this one. Is by a philosopher. You may have heard of Daniel Dennett, who is an American philosopher, and it's from 1987. Just to say that I think I told you because we tend to think that the world is we are making progress fast. I'm not so sure, because if you look carefully, it takes decades before, for example, neural networks proposed by Frank Rosenblatt in the 50s become useful and give the name of deep learning in the 10 years, year 2010 of almost 50, 60 years ago. So it took 50, 60 years to pass from the intuition, which was correct, to something useful and working. And here you see that in this paper, Cognitive Wheels, the frame problem in AI, you may remember that we quoted already this with the Voigt experiment of Simons and on the beach, probably already catches the problem, because it is this simple thought experiment again. So there is a robot which is going out of battery, and in a room there is a battery on a wagon that you see depicted here, taken from Rolf's book, from our body shapes of everything. And it has simple instructions to get the battery. So the robot is a naive robot, and it decides a plan which is formalized. This is a kind of imitation of a typical program that you write in symbolic AI. So you know that the robot is inside the battery, inside. So this inside R1, the name of the robot, room means go to the room. Then it's nice also the imitation of the AI language for doing these things. And then it perceives that there is a battery on the wagon, and then it takes out the wagon. Unfortunately, there is this ticking bomb on the wagon, and so the bomb explodes, and the robot and the battery are lost. Okay, so we need something better. Of course, I'm simplifying the arguments, but I really suggest you to read. May take a while to read it carefully, but I think it has a point. And so new version of a robot. Why this is interesting? Because it is what we do all the time. So you do your robot to open the valve, and it falls down. So you add a routine, because you check why it fell down, and you add a couple of routines, some thousand of lines of code to manage the strange imbalance that was actually making the robot fail. So in this case, we have a robot deducer. So this robot scans all the features of the environment, because we have seen before that focusing just on the battery, because the robot, because this is the point, no? The robot does what you program the robot to do. The robot is not able to, the mechatronic robot, the one that we have shown that was the same from ages to modern androids, only is able to do what it has been programmed to do. And this is, so it started to check if the color of the room changed when it takes out the room, what happens to the revolution of the room. So it has to consider all the features of a room. Of course, this takes a lot of time, and the bomb explodes. So at this point, it's clear that you cannot. So you cannot have a program which only focuses on what you have to do. So taking a battery, you need to think. This is the frame. You know, the frame is, for example, the frame of this building. So it's the context. So the frame problem is the context problem. So you are prescribing step by step what the robot needs to do. So you want to take the battery. The most natural thing is to tell the robot, take the battery out. But if there is a bomb and you don't know, and the robot doesn't know also, because it only knows what you tell it. So you need to consider the context. Okay, so you consider all what you can know about the context. This was the example 2. No, you cannot, because there are a lot of things in this room, for example. No? So what's the influence on pulling out the beer from the fridge of having a chair there? So if you consider, what happens is that you have so many objects in a room that if you want to consider the effect, and every object has a color, has a sound, has a smell, has a lot of characteristics. So the number of things in a context that you should consider is really high. So the idea of simply considering everything, is this influent? No, it's not influent, because this requires reasoning. So why the color of the bomb is not relevant? In some cases, it could even be relevant, no? Because if there is a small light, the fact that the light is maybe red or green may change. So there are a lot of things that you don't know in advance. So after so you have a model, only consider a task, and this doesn't work. This was example one. Then you have a second approach that you can take, and this approach is consider all the possible future in the environment and consider all what the influence on what you have to do is affected or not. This is also wrong, because it takes too much time. It takes a practically infinite amount of time. And so this leads to a third approach, because that's why I really like this Foyt experiment, because the first approach is, because the first was consider only the task and not consider at all the context. This doesn't work, because there might be a bomb. Second approach is consider all possible characteristics of the context, of the environment, of the framing of your problem. Not frame the problem, is the context of your problem, and you cannot do it because it takes too much time. The third approach is, okay, smart approach. So decide what is relevant and what is not relevant. But to decide that something is not relevant requires that first you check if it is not relevant. So the case 3 is not so different from case 2. It's the case 2 negated. So it's because more or less you're required to do the same amount of reasoning. So the point raised by Dennett was exactly this. So we consider, we give what the things that are obvious to us, but because we are a kind of entity floating over a very complex system, which is very integrated in our society. We don't even realize this. No, but when even a 10-year-old child already had millions of hours of interaction with other people, and already did a lot of random experiment, also known as play. They have played a lot. They have done a lot of useless things. So our consciousness is a kind of small layer above all these extremely complex systems. So what is obvious to us is not necessarily obvious, and it is not obvious for a robot. And if I wanted to do design a robot which is able to interact with me, or even worse, with an elder who has also some cognitive biases, problems, physical limitation, that's not easy at all. So the problem of the frame of reference problem is that this idea of driving the behavior of a system by a model representation of an environment is not probably going to work, if not in a factory. So why I'm very positive on Industry 4.0? Because in factories, I can decide the characteristics of the environment. And I can, so if you go back to this, if it is a factory, I know, me, designer of a factory, I know in advance what is relevant and what is not relevant. And by supervision, maintenance, we call it maintenance, I keep the environment as I want, with the characteristics that I want. And this is, means that in a factory, so in a controlled environment, in a structured environment, this approach can be basically not mitigated. You can exclude it because you control the environment. Of course, bridges collapse, factories fail sometimes, but with a lot of maintenance work, you can keep your model aligned with the environment. So that's why the current approaches can do a lot in factories. In general, in environments which are sufficiently structured, but they cannot really do what we expect from intelligent systems. So the idea is that we need something else. A deeply bio-inspired approach. This is actually what is already happening. So there is this kind of convergence between what the people is doing in the study of biological systems and what the engineers are developing on the other side. Increasingly, people is seeing robotics as a science. We have seen that this creates some problem because a cornerstone of science is to be able to replicate the results, and this is in robotics somehow difficult. We have seen that there has been significant progress also under this respect, and we have seen as how so a big question, if you want, is so this traditional approach that is symbolized by the robot falling of is okay, or if you need to think to an emergentist approach for robotics, and this is true for cognition and for also we have seen how now we are already starting to think about robots which are not rigid body of metals, but also softer bodies. The issue here is there are a number of theoretical problems. So how morphological computation works in terms of quantitative models, how intelligence and also meaning. So how a robot learn. So because one thing is to program the robot with a symbol battery. Another thing is the robot understanding what a battery or a cup of tea is by learning. And we need quantitative models if you want to build the systems. So, and this is the idea. So our idea, as you know, is to have to look at the agents as a physical embedded system, which implies a number of things, including the study of complex dynamical systems. We need to see not a poor symbolic approach, and not even a poor machine learning approach, but we need to let understand the intelligent behaviors of our interest. For example, grasping a beer from a fridge and taking me need to emerge from a system environment interaction, need to be based on large number of parallel loosely coupled processes, maybe even in the CPU or maybe on the neuromorph chip. And we need to be asynchronous because the world is asynchronous. And again, Industry 4.0 works because the factories are as we decided they are. And it needs to be coupled with the environment. We have seen the subsumption architecture. So it was, in the 80s, was an approach to mimic, for example, insect walking that was more or less in the same path, or even discovered work exactly like in the game This Robot. So I'm a bit accelerating because I'm a bit late. And of course, we have seen that this is not so obvious. So does this scale? So what works for a simple working mechanism will also work for high-level thinking. So the idea is that, okay, it's good for example, working. Not so, it's not obvious that it works for high-level thinking. The core, I would say that the core of this course is this one. So the fact that we don't only need the controller and the environment, but we need also to exploit the mechanical structure of the system. And we have seen that there are approaches, for example, in support or approaches based on information theory and so-called information self-driven self-organization. And this, just to, before going towards the end, so this is in 2 slides the state of the art. We have these humanoids, like the DARPA humanoids, which consume, for example, to work 10 times, 20 times as much energy as we use. And then we have these very effective robots in terms of energy consumption and working very naturally, but not so, not able to change speed or to turn. So if, for example, I hope I can show you. So you have this. So this is the famous passive walker by Andy Ruina. You see that this is a very simple structure. It has no control and works down a slope in a very natural way. Then you have other example. This is now a SoftBank Robotics robot doing the same thing. Okay, this is much more complex, and you see that it's not very, it looks not very convinced, right? You see, and it's very unnatural. And then you have this other example. Which basically on a single battery pack, this corner ranger robot, which is appearing from the left, is able to walk for 60 kilometers, which is a lot for a single battery. So this is very simple, very very effective, but so now I okay. But it has obviously limitations. So it is not. So it's not a robot. It's not a robot. It is a robot, but Sorry, don't look at the screen. So that's the big challenge. The big challenge is to be able to exploit the principle of corner ranger to build some robot able to do something interesting. Because it's nice to see the corner ranger walk down the slope, but it's not a lot. So carry on messages. We have enough problems to really hope that we do significant progress in robotics in the we cannot think, there are serious problems that were already clear to Dennett in the 80s that limit what we can do with the so-called advanced mechatronics. So the extension of a traditional approach, state machine plus actuators and sensor to robotics. Doesn't seem very likely that we have a companions robot meaning people entertaining old person. So we need to improve our methods because we actually, if you really want to give a serious answer to this question, so we really need a completely different paradigm approach. We need to do experiments. My personal opinion, shared by many, is that we will anyhow see that we need a new approach. So in practice, we can find out a number of guidelines. So we need to structure the living space, if you cities or houses, if you want to use robots. We will need a lot of operation and human supervision. We can, on the other hand, develop nice, for example, prosthetics instead can be developed because finally the difficult job of knowing what to do with this hand, artificial hand, is done by the human brain. So it's a kind of teleoperation. It's not obvious. So human in the loop is the key because cognitive capabilities are limited. And structurally, the environment is necessary because otherwise you fall into Dennett's fallacy. So we are good at doing robot in partially structured environment. It's time to go after the traditional disciplinary differences because for example, aging. The problem of aging, of course, can be solved by giving the old people some nice exoskeleton, but you can also work on the body of the elders with medical systems. And what is happening, that convergence that I was quoting, is that we tend to see the body as a very sophisticated robot, based on different principles. So the application of the principle that we are discussing are actually twofold. So on the one hand, in robotics, we tend to think that we should develop a robot with emergent intelligent behaviors coming from the sensory motor interaction with the environment. On the other hand, this same concept can be used to understand the immune system in humans, for example, which has a significant impact on aging. So, what we should we should basically study in this big area. Definitely, we need to do a lot of work on models on morphological computation. Is how the body thinks, so to speak, so the core of this lecture, and how system can self-organize. We need to improve a lot of experimental methods. So even under this respect, the way we measure the performance of robots will converge in what they do in medicine. In the meantime, and the Industry 4.0 example is really talking, we can do a lot of short-term application. But if you wish to see the robot of the science fiction, we need to do new things. I actually borrow from Josh lecture this slide, because if you think about where we are now, I would say most of the times is on the left. So we have disembodied intelligence. So we have a number of tasks that one by one, the tasks that we consider intelligent, are automated, like playing checkers at the beginning, playing chess 20 years ago, playing Go 2 years ago, computer vision almost done, especially for, let's say, slow, partially known context. And you see that all these lines are not on the same length. Natural language processing, okay, talk to any intelligent translator and you will understand why the line is right. Then we have what people is doing in the if you wish, the second wave, because I like this picture because this is the second wave is putting the intelligent task on a robot and perform the task. For example, object recognition. But still, you have a fixed embodiment. So the embodiment represents the structure of the robot. Where we are going with the third wave is able to do much more tasks. So is the diagonal of this cube. So that's it's first, second, third wave. So disembodied AI, rigidly embodied AI exploiting, for example, the configurability and the softness of the robot. And this requires morphological computation and the understanding, meaning developing working models of morphological computation and of self-organization. What's this link about? Because the popular, it's very popular today to talk about soft robotics. Because I come back to the example that I gave you of that I would like to see a passive worker working, being able to change speed and being able to work down. So to do more things, because those videos are interesting because the corner ranger and the passive worker are very effective in terms of energy. They move very naturally, but they can do anything more than moving naturally at a given speed. While the now robot, I had some fun from that video of now walking down the slope like the corner ranger, the Andiruina passive worker. It's very, consumes a lot of energy, but it does something. It says hello, it can grasp objects, it can do many things. What we miss to change speed, and this is the link with soft robotics. If I want to be able to change speed, I need to be able to change the configuration, because even from high school physics, so you remember the pendulum, the take what as an example. In the pendulum, the whole story boils down to the fact that given the length of a string connecting the mass to the pivot point, now the point where you attach the string, the period is fixed and it depends on the length of the string, and gravity, which is the same on Earth, everywhere, roughly the same. The simplest model of a passive working that you can have is this one in this picture. So is what is known as an inverted pendulum. The equations are more complicated and I spare you from seeing that. But again, there is a function which is linking the period, and so the gate. So in the case of a gate, the period is the period of this. And so the speed is linked to the length of a lens. This is, so that's why it's fixed. So what you need to be able to change the speed, for example, the minimum, legal minimum to say that you do something with your robot. You need to be able, like in Fumiko Asano example, to change the configuration. The minimum that you need is a mean. And we have more than needs. For example, here we have a lot of articulation, and they are compliant articulation. This is what exactly allows us to have complex trajectories in there. So actually, morphological computation and soft robotics are really linked. Actually, morphological computation and some kind of self-organization are needed to be able to make a robot work. But also, if you want to exploit passive dynamics, you cannot do it with a rigid structure. So this is it's really an important aspect, because shows that as told before, like everybody, I expect a lot of progress in robotics, no? But the real promise of robotics will be possible so we will be able to exploit it only if we understand these things. This links very naturally to today's lecture, because actually we need mechanicists to engineer this self-organization. We need new platforms. One of the approaches is actually the approach that Julia is going to talk to you about, which is implementing neural dynamics on a neuromorphic computing on a neuromorphic architecture. So I'm very happy to see Julia. And
can you hear me?
I already introduced her at the beginning, and so I'm happy to give her the floor. So welcome, Julia. The floor is yours.
Thank you. Let me see. Just a second.
Yeah.
Can you hear me? Can you hear me?
Yes, perfectly.
Okay, great, perfect. Sorry. Yeah, welcome. So I think we have something like 20 minutes now, right? Maybe 22.
You can take more.
Okay, okay. I will probably have to leave, so I'm at a conference myself now. Okay, so I will share my screen with you and then we'll just start right away. How about that? So let's see, where is my talk? There it is. Share. Can you see the screen, the lecture? Or maybe start it. Okay, can you see the slide?
Yes.
Okay, can you see my mouse?
Yes, I also see your mouse.
Okay, I will use it as a pointer. All right, so the topic will be neuromorphic computing. So I'll tell you a little bit about this new type of hardware, computing hardware, that's emerging and that people use to realize neuronal models and neuronal systems in an efficient way. I'll talk about embodiment, and that's probably also what Fabio has mentioned a lot, I guess, in his lecture. I only listened to the very end of it. Of cognitive neural dynamics. So I've added this word cognitive to neural dynamics because this is what makes our neural architectures particular. So we try to actually model cognition. And what I will start with is trying to define the word cognition. Now, cognition is one of these words, together with consciousness or even intelligence, that people discuss a lot about their definition. Now, you can discuss for decades and never agree on one. So I won't give you the definition, but I will try to give you some intuition of what you can call a cognition. And I will start with a story. For me, it comes from Mark Bickert. He has a few books on what he calls interactivism, so a particular view on cognition or cognitivity, how it emerges. So which system will we call a cognitive system? And let's have a little thought experiment. Let's think about a bunch of bacteria. Let's see if this movie can run. The movie is just to have something in the background. Two types of bacteria. One bacteria can just move along the sugar gradient. It always goes to where there's more sugar. Nice strategy if you were a bacteria eating sugar. Now imagine there's another bacteria that can do two things. It can go along the sugar gradient if it points in the right direction on this gradient, or it can turn around if it doesn't, to find the direction in which the sugar gradient will go up. So we could say that the second bacteria is more cognitive than the first one because it can decide between two options what to do. And this is the first step towards a more cognitive behavior. So the important part of cognition is the ability to make decisions. To make decisions, you need to have several options that are available to you and the ability to choose between them. Now, it's not enough to just make decisions. You want to make smart decisions. So what can help you to make smart decisions that help you to survive better? So memory helps you to make smarter decisions. Why? Because you remember, you not only see what is currently on your sensory surface, but you remember what has been just a moment ago, or maybe longer ago. So if it's just a moment ago, then we're talking about working memory, just the immediate memory of what has been just before. So this will help me to compare different options that I have. So I can perceive one option and the second one and the third one, and then look at all three of them and then decide between them. Form heads help you to more efficiently generate writing or write skill control to be all motor effective. In some episodes, good thing to make language representative objects or relations between objects. So basically, this is like a short story of the whole cognition. You start with the ability to make simple decisions. Do you still hear me?
Yes, yes, yes.
Okay, great, because I disappeared from my own screen.
Yeah,
so
I removed the video because there was some problem with the audio.
I see. Okay, my connection is unfortunately not perfect. Let's see how it goes. So from the ability to make simple decisions to make more and more complex decisions. Biological system. And what does it mean to biological system? System evolve to produce behavior. And the adapters is really learn from biological systems, generate behavior. Now let's cognition. So the first step to cognition is to evolve. Now let's see how it can be done in the neural system. Because cognition is realized in nervous example of a system that can behavior. This example from a neurophysiologist Bright, who made thought experiments, what he called synthetic psychology. So he was thinking of the simplest possible system that can generate behavior. And he said, in order to generate behavior, you need 4 things. First, you need a sensor to sense the currents of the environment. Second, you need a motor system to produce behavior, right? And move something around. Now, importantly, you need a body that will put 2 together. So that your sensors can affect your motors, and then your motors will move your sensors along. So you need to connect them physically. And then he said, yes, you need a neural system to produce behavior, but the neural system can be very, very simple. It can be as simple as just 2 wires connecting your 2 sensors to 2 motors. How can you produce behavior with such an organism? Well, if you have a localized source of light somewhere in the environment, then one of your sensors will receive more light than the second one, which means that one of the motors will rotate faster than the other one, and now your animal will turn away from sources of light. So it can produce somewhat intelligent behavior, avoiding light, with a very, very simple neural system. Now, if you want a different behavior in this framework, then you need a different neural system. Like, for instance, having 2 wires that cross instead of connecting sensor to the motor on the same side. If you have the connections crossed, then you will have an agent that approaches light, that likes light, that always goes there. Now let's try to formalize such a system. How can we mathematically capture behavior like this in such a simple agent? One way to formalize it is the following. So we can describe the state, the behavioral state of the agent with something people call behavioral variable. If our behavior is just driving around in an environment, then such a behavioral variable could be the heading direction, in which direction our agent points. And now if you set some constant speed, then the direction of movement will determine your behavior, where the agent is going. Right? So you have some variable that describes the behavior. Now we can write down an equation that describes the rate of change of this variable. Right? The rate of change, phi dot, so like the temporal derivative, is equals to something. Now, if we like let's say on our computer, solve this equation numerically over time, then we get the temporal evolution of phi. So for every moment in time, we prescribe certain phi to our system that can either describe what our system is doing or dictate what our system should do. Now, people have figured out that for biological system, such behaviors correspond to an attractor of the dynamics. What does it mean to be in an attractor? Attractor in a dynamical system is a state to which your trajectory will converge if you start somewhere in the vicinity of this attractor. The equation mathematically will have a form like similar to the one that you see here. So phi dot is equals minus phi plus a. If you solve this equation, then your solution will have a form of over t, meaning that as time goes to infinity, your phi function will converge to a. So it will kind of converge to a and then get stuck in a. So it won't so easily leave your attractor state. Why is it important? It is important because, remember, you perceive the situations with sensors. Sensors tend to be noisy. Second, you control your system with neuronal system. Neuronal system also tends to be noisy. So in order to produce behavior reliably, it's important that the neuronal system sits in an attractor. It gives you the stability in dealing with noisy sensor inputs and noisy computing system. Good. Now, we have said that the situations become interesting if you have a choice, if you can do different things. So let's see how in this framework we can represent multiple targets. So what happens if I have multiple targets? What happens that now it's not enough for me to just have my behavioral variable, just a single value, because I somehow need to represent multiple values and represent something like their utility, how good or bad my choices are. I still need to make decisions based on this utility, and I need to stabilize them. So from the dynamics that will describe the behavior of my variable, I go to dynamics that describes behavior of some activation function, which represents utility of different options. And this is the step where we go away from behavioral dynamics and go to neuronal dynamics. Because what our neuronal brain dynamics do is to represent utilities of options and prescribe dynamics for them and make decisions based on them. So let's now look at one model, one neuronal model that does that allows you to represent utility of different choices and make decisions based on that. First, a little historical note where this model and this equation that I'll show in a minute comes from. It comes from biology. So people were measuring activity of large neuronal populations in different parts of animal brains. So here I show activity recorded from motor region of monkey, so premotor cortex. Monkey is doing a reaching task. So it starts somewhere, in the center of its visual field, and then it does either reaching or saccadic eye movements to different targets in different directions. So we can characterize this behavior by the direction of movement, similar as was for our vehicle. Now what people do, they measure activity of neurons in premotor cortex, and for each neuron, they determine how active this neuron is for different directions, for all possible directions. And you get these green curves, some Gaussian curves. So for one particular neuron, it will react most strongly to a particular direction, maybe 180 degrees, and then less strongly to nearby directions, and then it won't react at all to faraway directions. So you measure these so-called tuning curves for every neuron, like 100 neurons, and you just do these measurements for all directions of movement. Now what you do then is you make another experiment, and then for a particular movement, let's say, here maybe like 170 degrees or 190 degrees, you measure activity of every neuron. And now you scale the tuning curves measured in advance with activity of the neurons in this particular experiment. And you get the blue curves, right? They're scaled versions of the green curves, and the scaling factor is activity for a particular direction. Now what you can do, you can sum all the blue curves, and you get one curve, so one function that describes activity of large neuronal population. People call it distribution of population activation. So it's a single function, and it describes state of a large population of neurons. Can you still hear me?
Yes.
Okay, great, because the videos are frozen. So what you can do now is you can perform your experiment. In your experiment, you show the target, there's some delay.
Well.
They describe how this activation function evolves over time. And they come up with a particular equation. I'll go in detail through this equation in the next slide. So here's the historical note. So people like Mark of equations in 1977 and even before, Wilson and Cowan have just came up with this equation. So came from the sky more or less, very simple form. Activity of large neuronal inside this field. You can find it under the name of winner-take-all architecture or bumper tractor network. So what does this equation consist of? So first we have the U dot. Remember, we have a tractor, we have the dynamics, so we have activation function, we have this U dot. U depends on X and on T. T is time. X is our behavioral variable. So maybe it's the direction of motion, let's say. Something else, could be color, could be position of your motor system, some behavioral variable. Now over this behavioral variable, we define a function that describes the utility, like the quality of different states. And this function follows this equation. We have four terms. The first one is minus U term. It tells us that this function has an attractor, and attractor is determined by the three other terms. The first one, H, is a negative resting level, just to put this thing below 0. I is input, coming maybe from sensors, maybe from another neural field like that, from somewhere else in the brain. Now the interesting term is this integral in the middle. This integral describes interactions within neural field. It has two components. One is the omega. It's called interaction kernel. This integral is a convolution, meaning that this interaction kernel is shifted along the x dimension, and it always multiplied with the function f of u, and then summed with the next multiplication. How convolution works. What does it mean? It means that every position on this field interacts with its neighbors in the same way. So it's homogeneous, the interaction. How does it interact? Well, as this kernel prescribes. This kernel has a positive part for small delta x, right? So if two nearby positions, they excite each other and they inhibit everyone else. So each position excites its neighbors and inhibits everyone else in the field. So that's why it's called winner take all, because these nearby positions, they will pull each other high and they will inhibit all the others. And there will be competition in the network on a large scale. Now, what does it mean that two positions are close to each other? They're close to each other on this behavioral dimension, meaning these are the neurons that encode similar things, similar directions of movement. So your neuron encoding 55 degrees will probably excite neuron encoding 54 degrees and 56 degrees, but will inhibit the neuron that encodes 30 degrees. So this is what this kernel means. Now we have another function here, f of u. So f is so-called output function. This makes this equation nonlinear. So you have some nonlinear sigmoidal or step function that tells you if u is below 0, then this interaction term goes to 0. It doesn't play a role. Your field will just repeat whatever input tells it to do. However, if u is above 0, all right, so if your I is larger than your resting level, so your u reaches the 0 threshold, then f converges to 1, so it grows and grows and maximizes at 1, meaning that this interaction kernel then comes into play. So what does this dynamics, this equation give us? I'll now let the field evolve. There is some simulation solving this equation. Let me see. So the blue line is our u function, the green line is the input, the red line is the f of u, the output. So what you can see, there are two inputs presented to the network. They are approximately equal. Now the network, because of noise, selects one of the inputs. One of the inputs passes the activation threshold first, the interaction kicks in, the nearby sites, the excitement, and they inhibit everyone else, so that the second input just gets inhibited. Now, this is important because now the network has made a decision for one of equally good inputs and has stabilized this decision. Now, we have noise in the system. If we won't stabilize our decision, we would switch from one to another, but we don't do it because of these dynamics, because of this Mexican hat winner-take-all dynamic. We can make our decision. And this is important because if you have two equal options, you don't want to switch between them. You want to select one of them and you want to stick to this decision. You want to make something about this decision, maybe execute an action. Maybe it was a wrong decision, then you get your negative feedback, and next time you weigh your decisions differently. Important to stabilize. Something else happened here. At the end, the green input over our active location went back to 0. We took away the input. However, the activity of the peak is still there. Because of this positive part of the interaction kernel, the activity is reverberating here. So the neurons, they excite each other, and this excitation is strong enough to keep them active. What does it give us? It gives us a model for working memory, because now I can present the input, I can take it away, and activity will still be reverberating. And remember, the working memory was an important first component that made our systems more cognitive, more interesting. So what does this neural dynamic give us? Let's see some cognitive properties of neural fields like that. First, they provide the detection and forgetting instabilities. What does it mean? This moment when a noisy input reached activation threshold and a peak was formed is an instability in the dynamics. What does it mean? It means that if I now remove the input, the system will have some inertia. It will tend to stick in the active state. There will be a hysteresis, people say. So there's really an instability that separates an inactive and active state. And that's important because now as a system, I can differentiate the states when I don't detect anything interesting and when I've detected something interesting and can act upon it. What these instabilities also do is that they discretize continuous time into discrete events. When I have detected something, when I've made a decision to move my end effector. So this is the first important property. Second, my output of the field are these localized bumps. Because of the winner-take-all structure, there's always some localized bump formed. What these bumps do is that they discretize continuous space of my behavioral variable, direction is some continuous dimension, into discrete categories. And these categories have meaning. They are now finite, they have finite width, but they are not just equally sampling my space. They sample my space based on experience, based on the peaks that I have formed previously. Second, if I have several inputs, or third, if I have several inputs, then I can select among them and I can stabilize these decisions. This was an important step towards being cognitive. And I have a model for working memory, so I can form this sustained activation. So what it allows me to do is to use these neural fields as building blocks in order to build architectures that can now solve more or less complex cognitive tasks. I won't go into much detail, but I will just show you, flash a few such architectures later. However, let us first solve one problem, because the fact that the peaks that the neural field forms are attractors is problematic. Why? Because attractors are stable states. What does it mean? If you get into a stable state, you never leave it. That's why it's attractor. It's like a little magnet that keeps you there. So now let's imagine we have some sensory motor system. We have a bunch of motor and perceptual dynamic neural fields, right? They can be one-dimensional, is the color dimension. They can be two-dimensional, is maybe the position of my hand, of the end effector in space, or location of the target on the retina. Or they can be three-dimensional, like linking space and color, for instance. All great. But all these fields, they form these peaks. The peaks are attractors, and the situation never changes if something doesn't change in the outer world. So it's a problem. And it's not a problem that I won't be able to move, because a stable state like this can correspond to movement. But remember, for the Breitenberg vehicle, if I have a peak at a certain orientation, I will move in this direction. So that's fine, because movement corresponds to attractor. However, once in a while, I want to do different things. So I need some mechanisms that will allow me to destabilize attractors, to get out of them and do something else. And I will cut the long story very short here and just send you to one of the papers of mine from 2010, and there's another one from 2018 that introduces such a mechanism, how to switch between different attractors. Here, just in a nutshell, so it's kind of requires a few steps to do that. Like first, we need to represent different attractors. So we have a number of nodes which I can activate in a sequence. Each of these nodes will create some attractor pattern, maybe some peak in one neural field, maybe a number of peaks in many neural fields, and these peaks will then lead to some behavior by the motor system, and I can monitor how this behavior is executed. Now, what is important that at some point I detect that I'm done with whatever the goal of my action was. And I do it in a condition of satisfaction field. So the term has something to do with the theory of intentionality of Searle, who said every action, whatever do, and some mechanism to check I have achieved this goal now. So this is what the condition of satisfaction field is doing. It receives some input from the action field about the information. What shall I anticipate when I'm done with this action? And it also receives some sensory input and performs a matching operation. So when whatever I sense corresponds to what I anticipate to be at the end of my action, then the condition of satisfaction is active and inhibits my current attractor, allowing me to move forward to the next attractor. So this is just another another building block that I can use to build neural field architectures. So here, like a little overview, and I would again send you to the webpage, sandomirska.eu. There are examples of papers if you're interested of what one can do, what architectures one can build with these neural fields. And one of them is about action selection. So it's an architecture that has different elementary behaviors, one for looking for different colors in the visual field, one for moving the head of the robot, moving the arm of the robot, and opening and closing its gripper that allows the robot to manipulate objects on the tabletop. Another one is about planning action sequences. Another one is about learning to perform precise saccadic eye movements. Another one is for learning sequences or haptically learning to represent objects. Just to give you a feeling that you can now use these neural fields as building blocks of architectures. How much time do we have? Probably not much, never mind. Now, but there's a problem. If I build these architectures and if I simulate them on a computer, look at now, okay, 3 minutes. Okay, just a brief note. Then there's a problem. Okay, so if I take 5 more minutes just to give you a brief overview, and then maybe if I can now share this, yeah? So just the problem, just to introduce to you this neuromorphic part. If I try to simulate such architectures on the computer, then there's a huge mismatch between the way how these architectures work, highly parallel, moving around analog values of these continuous variables, with close interlinkage between memory and computation, if we implement them on a regular computer, then there's a huge mismatch. The computer uses these digital representations with fixed precision. It's based on sequential processing. You constantly go back and forth between memory and processor. Because you have a separate memory unit. So it just runs slowly and super inefficiently. That's why now in my work, I tend to use neuromorphic hardware. And there are now a few chips, devices that use neuronal principles as their building blocks. So how does it look approximately? So people have studied what the neurons are doing on the lowest level. And the neurons seem to accumulate inputs as analog variables, and then when these accumulated input reaches some threshold, they do something known as a spike, very brief increase in their activation, like a pulse. A neuron seems to communicate with such pulses. So what people manage to do is in using digital or analog electronics to mimic the dynamics of a neuron like this. And now what they also managed to do is to put 1,000 or 1,000,000 of such neurons into a hardware device. So what you get now is like a little piece of cortex with spiky neurons that you can program. How do you program these neurons is then the question, because you don't write C or Python code to program them, right? You have to use some neuronal models to do that. So since we have our population dynamics in neural fields as the neuronal model that describes how you with populations of neurons, so what we try to do is to use these neural fields as a programming language for such neuromorphic devices. And I will just show you maybe how to implement a single neuronal field, and then you can imagine how to implement all the rest. I will just flash maybe a few examples. So if you look at the inside, then these triangles here on the right are the neurons. For instance, on a little device that I have worked with for a long time has 256 neurons, not too many, but we have X number of neurons, usually represented as a vector. Then each of the squares are synapses, are connections between neurons. And you have in this device 2 sets of synapses. Half of them are non-plastic. These are the ones that I can set, that I can program. I can program my architecture, my neural architecture into the device by setting these synapses to certain values. And half of them are plastic. So this one I can activate, and then they will follow certain learning rule and will change their weight depending on activity of the neurons, of the pre- and post-synaptic neuron. So, it uses analog circuits and digital communication with spikes. Programming this device means wiring up the neurons, so telling which neuron should be connected and which not, and setting the parameters. So let's just have a look how a neuronal field would look like on a chip like that. So neuronal field, remember, has these positive connections to neighbors and negative connections to everyone else. These negative connections can be realized through a dedicated inhibitory population. So there's a little neuron, it gets positive input from everyone and inhibits everyone back. So if I have a little architecture like that, I can translate it into connectivity metrics for my neurons. So, these are the neurons. These are the connections. So the red squares are positive connections. Each neuron has a positive connection back to itself and to its neighbors. Here only 2 neighbors, maybe in reality will be a bit more neighbors. It has also a positive connection to these inhibitory neurons. So 2 neurons I declare the inhibitory guys. Everyone excites these 2 inhibitory neurons. And these 2 inhibitory neurons, they in their turn inhibit everyone else. You see, very simple. I just create this connectivity matrix in whichever programming language I want, Python, C++, MATLAB, or whatever, and I send it to the chip and I wire up its connections. Then I can plug out my computer and my chip will realize a neuronal field. How can I check it? Well, I can record its activity. I can provide some input. So the input needs to be spiking. So it's just these little pulses. And let's say there are 2 connections that receive a bit more input than all the others. And this will be the output of the network, where the network formed a peak over one of the inputs and inhibited the other one. Yeah, so what one can do now is to realize different architectures. Now, remember the sequence learning architecture? I've shown it briefly. We can realize it with a connectivity matrix, put it on the chip, and make the chip learn a sequence of behaviors. Here on a very simple example, we have 2 robots. One shines its laser pointer to different positions now in front of the other robot, and this robot learns the sequence of positions. What does it mean it learns it? It means that it stores these locations in plastic synapses that connect the ordinal nodes. So I have some populations that represent the first, second, third, fourth, fifth item in a sequence, and the content nodes. And the content nodes this violet region on the spike train plot, they represent the position, right? So this would be more to the left, and this one more to the right, and this one more to the left again. So my memory for a sequence is a few associations between the ordinal nodes 1, 2, 3, and the positions here, there, and here. So what I can see now, this is the visual input to one of the one of the robots. It sees some laser here, laser there, laser there. This visual input drives our content neural field that also replicates these positions. And as long as one of these ordinal nodes is active and the content neurons are active, the connection between the two is strengthened according to this neuronal plasticity learning rule. So, this connection will then grow. And then here between these two regions, connection will grow, and between these two regions, connection will grow. So now in the reproduction of a sequence, I just activate the first ordinal node, and it will activate the correct position in the content field without any visual input. So I can reproduce the sequence. One simple example. Another more complex example, what I can do, I can replicate some neuronal studies in animals and rats that do navigation. I don't know if you follow, but there was this famous work for Nobel Prize for discovery of place cells and grid cells, so the cells that respond to different locations in an environment when rat navigates to this environment. And many people were developing architectures, neural architectures that do that kind of help an animal or an agent to navigate in the environment. And some of these cells are head direction cells, so they represent the direction, like remember our Breitenberg vehicle in the very beginning, so you can have a little neural architecture that tracks the orientation of the animal based on its motor signals. So it can represent the orientation as path integration, people say. This architecture looks like this. We put it on a chip and it works. We just skip it a little bit. Now, we can do this tracking of orientation in 1D, but we can also do tracking of position in 2D. Again, on a neuronal chip. And if we can do that, then we can also represent, let's say, collisions with walls. Right, and then what we can read out from plastic synapses on chip is a little map of collisions. So let's maybe show it like here, right? So like these blue dots, this would be map of collisions. So if you change environments, then on the chip you can represent different environments. Let's see, I'll skip the reference frame transformation, although it's maybe an interesting story. The story just goes some things are easy to do on a computer. For instance, to calculate a reference frame transformation, you just need to do a minus operation. That's easy on the computer. How do you do minus operation with populations of neurons? It's not trivial, but there are architectures that can do that. And if you know these architectures from talking to your neuroscience friends, then you can also implement such operations on your neuromorph. You have the references, you can look it up. Now, these few architectures that we have implemented, they represent fundamental building blocks. And I will just skip quickly. So if we implement this Breitenberg vehicle, then we know how to generate attractors in the sensory motor loop, one building block of a cognitive architecture. If we know how to do reference frame transformation, then we have a very important building block to link all kinds of sensory motor spaces that are important for behavior production. When we do this navigation and map formation called simultaneous localization and mapping, then we solve two fundamental problems in cognition: state estimation, where I am now, where is my hand, what am I perceiving now, and building of representations. These representations can be of an environment, they can be of an object. Also, it's an important component of any cognitive system. And finally, if we can do adaptive motor control, as on a slide that I haven't shown you, then we can move reliably in an environment. So these are all important building blocks. So what would be the take-home messages? Just a few. So first, embodied cognitive computing requires two things: decision-making and memory formation. If you have these two, then you can build a cognitive computing system. These two properties can be realized in neuronal dynamics. What does it mean, neuronal dynamics? It means some neuronal network that has recurrence, that has feedback connections. You cannot realize decision-making architecture with memory formation in the feed-forward neuronal network. You need recurrency. Now, these neuron dynamic recurrent architectures, they can be realized with spiking neurons. They can also be realized with continuous dynamics. Just feel free. And depending on whether you want to do it in real time, you might want to use specific hardware to do that, and you might want to match the hardware that you use to the computing architecture that you use. If you interface such neurodynamic architectures to sensors and motors, then you get embodied neuromorphic cognitive systems. So embodied meaning that they're linked to sensory information and also to motor system. Okay, so herewith I end. I will just thank all my students and collaborators who contributed to part of the work that I practically didn't show you, just flashed. Thank you very much.
Thank you, Julia, for this great presentation.
Thanks.
I don't know if there are questions now. Probably no, because it's a bit late.
Yeah, you can send me all the questions per email.
Yes, yes, as Julia is saying, I think she will be very happy to answer to any question you may have. What I really wanted to underline, because intentionally we left to the latest lectures the more technical but also more advanced results. You see that those ideas that 10 years ago when the Shanghai lecture started were a bit of embryonic, now are really becoming things on which you can work. And I think that the work that Julia is doing is actually extremely relevant to our field, to the field of embodied cognition. So if there are no questions, as I fear, I apologize with Julia because we started a bit later, and so. But I think that we got the message, and I hope that this is just the starting point for your own thinking and your own study and your own research. So.
Yeah, thank you very much. It was nice meeting you. Sorry also that I had to shift it so a bit later and that I have to run now. Yeah, but feel free to write me an email. Okay. Google for our work if you're interested in more details.
Yeah, very interesting. Thank you. Bye.
Yeah, thank you very much. Bye-bye.
Bye-bye. So I just wanted to say goodbye to everybody. And see you next year. So next year will be 10 years of Shanghai lectures. I really think that we can appreciate the progress that has been done in these latest 10 years. And of course, for next year we'll try to organize something adequate to the 10 years celebration. And actually, we are already working to connect to organize the lecture for next year. Thank you again for attending yet another lecture, and see you next year. And keep in touch. And please send any question or even research proposal or problem proposal that you may have. Thank you, and see you next time.